Have you ever just stopped and wondered, how do we think? Not what we think about, our grocery list or some big project, but the actual architecture, the blueprint for thought itself. Well, today we're going to dive into this really powerful idea from math and computer science that, well, it might just be the answer. It gives us a peek into the very structure of the mind. All right, look at this number, 86 billion. It's a huge number, right? Almost impossible to really wrap your head around. And that is the estimated number of neurons you have packed inside your skull. But honestly, that number, it isn't even the most mind-blowing part. Now, the real question is, how do all those neurons, with their 100 trillion connections, organize themselves to create, well, everything? Coherent thought, consciousness, your experience of the world right now? How does this incredible biological computer manage all that information? The answer, and this is where it gets really cool, might be something surprisingly simple and elegant: a graph.
So this brings us right to the heart of the matter. We can call it the brain's information problem. Because that scale, that massive number of neurons and connections, it isn't just a cool trivia fact. It's a fundamental logistical nightmare that any theory of the mind absolutely has to solve.
I mean, just think about it for a second. Your brain can't just operate like a giant spreadsheet, right? A flat list of every single belief you have. The sky is blue, it's currently Tuesday, coffee is amazing. Why not? Well, because all of those beliefs are tangled up with each other. Your belief about the weather depends on what season it is. Your belief about the season depends on the month. If you had to check every single belief against every other belief every time you learned one tiny new thing, your brain would just grind to a halt. It's computationally impossible. No, the brain needs a system. It needs an architecture.
And that, right there, brings us to the proposed solution. To handle this incredible web of dependencies in an efficient way, the brain might be using a very specific kind of mathematical graph to organize everything it knows. And this structure? It's called a factor graph.
Okay, so what in the world is a factor graph? The easiest way to think about it is like a cheat sheet for a ridiculously huge probability problem. Instead of one single tangled-up equation that's impossible to solve, a factor graph lets you break the problem down into a bunch of smaller, bite-sized local pieces. It has two main components. You've got variable nodes, these are the things you're trying to figure out, and then you have factor nodes, these are the rules that connect all those variables. All right, let's actually build a super simple one in our minds. The circles you see, those are your variables. Let's say season and weather. The square connecting them, that's a factor. It's just a rule, something like if the season is winter, then the weather is probably cold. Now, here's the most important rule of the entire system, the golden rule. Circles only connect to squares, and squares only connect to circles. You never, ever connect two variables directly. And that simple, disciplined rule, that's the secret sauce. It's what prevents a total computational meltdown and makes the whole thing work.
Okay, so now that we've got the basics, there's this really clever twist called a Forney-style graph. It basically flips the whole thing on its head. So instead of the nodes being variables, the connections, the edges between the nodes, those are the variables. The nodes themselves become the factors, the rules. So why do this? Why make this change? Because it's absolutely brilliant for modeling anything that unfolds over time. Suddenly, your whole state of mind, your collection of beliefs at this very moment, can be represented by an edge flowing from one factor, one moment in time, to the next. The graph's structure literally starts to look like the arrow of time. It's so elegant.
Okay, so we have the structure, right? We have the blueprint. But a blueprint isn't a building. It's just a plan. So the big question is, how does a factor graph actually do anything? How does it, think? The answer lies in this beautifully simple process of local communication. This process is called message passing, and it's exactly what it sounds like. I want you to imagine each node in our graph is a person in a massive, crowded room. They're all trying to solve a giant puzzle together. Now, instead of chaos, everyone shouting at once, the rule is you can only pass a note, a message, to the people standing right next to you. Your neighbor gets your note, combines it with the notes from their other neighbors, does a quick calculation, and then passes a new, updated note along to their neighbors. And just through this simple chain of local, private conversations, a globally correct answer starts to emerge. It's incredible. So the specific algorithm that does this is often called belief propagation. And it's really just a repeating cycle.
A node listens to the messages from its neighbors, it does its own little bit of math based on those messages and its own rule, then it sends out a new updated message to its neighbors. And this just happens over and over and over again. These beliefs spread through the graph just like ripples in a pond, until eventually the entire system settles down into a single, stable, coherent interpretation of reality. And this is the absolute key insight. This whole architecture explains why the brain is a network, why it's a collection of parallel processors and not some single central CPU. With this system, inference, the act of thinking, becomes distributed. It becomes local. A tiny little cluster of neurons doesn't need to know what's happening on the other side of the brain. It only needs to talk to its immediate neighbors to play its part in a massive brain-wide computation. It is decentralized intelligence, pure and simple. Now, I know what some of you might be thinking, especially if you know a bit about neuroscience. You're probably saying, hang on, this all sounds way too neat and tidy. The brain isn't clean. The brain is messy. It's famously full of feedback loops. And yeah, you're right. And that introduces a really big problem for this beautiful model. So let's just face it head on. The brain's networks are packed with these recurrent loops, where a signal can travel out and then circle right back to where it started. So in the nice, clean world of message passing we've been describing, isn't that a total disaster? The short answer? Yeah, it absolutely can be. Loops can cause these messages to just echo. They get stuck in a feedback loop, bouncing back and forth forever, so the system never settles on a stable belief. Or even worse, it might settle, but on the wrong answer. Or maybe it could settle on different answers depending on where you start. Basically, loops make the math a total mess and make the whole system dangerously unpredictable. But, and this is the really amazing part, the brain's own architecture seems perfectly, almost intelligently designed to solve this very problem. For one, it's hierarchical. Information tends to flow much more strongly forward than it does backward, which naturally dampens those echoes. Two, it's sparsely connected. It's not just a big ball of tangled wires. That sparsity limits how many nasty loops can even form. And three, the neurons themselves have a kind of natural damping built in. So it turns out that the very features of the brain that we called messy, they might actually be the elegant built-in solutions that make this whole system possible in the first place. Okay, so let's take a step back and pull this all together. We started with this huge problem of scale. Billions of neurons, trillions of connections. And we've walked our way to a specific computational architecture that seems to map just beautifully onto the actual structure of the brain. But the picture still isn't totally finished. We have the why, this guiding mathematical rule called the free energy principle, which we can think of as the brain's deep desire to minimize surprise. And now, today, we've talked about the how, the factor graph architecture. And when you put those two things together, what you get is this incredibly powerful framework for understanding thought itself as a process of local, distributed inference. It's how every tiny part of your brain can work together to create one single, coherent reality. But as powerful as that is, we're still missing one crucial piece of the puzzle: time. A static blueprint, a static graph, doesn't capture the whole picture. Because our minds don't just reason. They reason at a ton of different speeds, all at the same time. You know, we can process the flicker of a candle in milliseconds, but we can also ponder the meaning of our lives over years. How does a single architecture handle all those different rhythms of thought? Well, that's a story for another time.